This is Related Rates 2, Trimester 2, Day 16. Problem number 1. A ladder 15 feet long is leaning against a building. The bottom of the ladder is moving away from the building at a constant rate of 2 feet per second. This will be for both parts A and B. So we have a building. We have the wall of the building. We have the floor of the building. And we've got this ladder that's leaning against the wall. It's reasonable to assume a right angle for this model. It's a 15-foot ladder. That's not going to be changing. That's a constant 15 feet. The bottom of the ladder is moving away from the building at a constant rate of 2 feet per second. And we'll want to put some labels on the sides, X for a horizontal distance, Y for a vertical distance, and Z for that hypotenuse. So that 2 feet per second is the dx dt, how the length of X is changing with respect to time. As moving that way, X is getting larger, so we can say that dx dt is a positive value. We want to find the rate at which the ladder is moving down the building. We want to find how y is changing. Find dy dt when the ladder is 9 feet from the building, when x equals 9 feet. We need an equation that will connect x, y, and z, x and y because we have information about them, z because we know that length, y because we're interested in finding dy dt. So we'll go back to our Pythagorean theorem again, x squared plus y squared equals z squared. The one little piece that I'd like to introduce today is that if we know that something is not going to change over the course of the problem, so in this case our z is not changing, it's the length of the ladder is not going to get longer or shorter, we can go ahead and plug that value in now. X squared plus y squared equals 15 squared. I wouldn't plug in this 9 feet for my x value because that is changing. The ladder is sliding out from the wall, so the distance at the bottom of the ladder is from the wall is going to be changing, so I'm not going to plug that in yet. I'm going to go ahead and take the derivative and have 2x dx dt plus 2y dy dt equals 0. Now, if I hadn't plugged in this 15 for my z, when I take the derivative, I would have had 2z dz dt, but the dz dt equals 0 because z is not changing. That's why we can go ahead and plug this constant in now because I'm going to get a 0 anyway. So I've got my derivative. Might like to simplify. I can divide each side by 2. So I have x dx dt plus y dy dt still equals 0. Those are in my always equation and derivative box. Then I'm going to say, okay, well, at this moment in time, what's going on? Well, at this moment in time, x is 9. dx dt is given as 2. Y, don't know why, but dy dt is what I'm trying to find, and that should equal 0. So I'm going to come over to my side box here. I'm going to say what's going on at this moment in time is that this triangle is still, my ladder length is still 15. My x at this moment in time is 9, and this is my y, so x squared plus y squared equals z squared. 9 squared plus y squared equals 15 squared. I get y squared equals 144, or y equals 12. I could also see that that is a 3, 4, 5 right triangle and recognize that that's a 12. So I've got dy dt equals 9 times 2 negative over 12 equals negative 1.5. And I need some units. The length of y is measured in feet. The unit of time is seconds. So dy dt equals a negative 1.5 feet per second. Well, why is it negative? It's negative because this length y is getting shorter. If my distance, if what I'm measuring is getting smaller, then my rate of change is a negative number. So the negative 1.5 feet per second makes sense. For the part B, find the rate of change of the area of the triangle formed by the ladder. So I still have the same diagram from above. I can still use the same picture. But what I'm finding now is I want to find the rate of change of the area. So how is the area changing? D what dt? dA dt. A for area. The triangle formed by the ladder, the building, and the ground, when the bottom of the ladder we're still looking at when x is 9. So back to our equation again. Pythagorean theorem isn't going to help us here. We need an area equation. Well, geometry tells us that the area of a triangle is 1/2 base times height, which is all well and good, but we've got x, y's, and z's, so we want to put it in terms of our x, y's, and z's. 1/2, our base is x, and our height is y. So from there, we're going to need to take a derivative. You can multiply each side by 2 if you really don't like fractions, but I don't think there's any reason to do that. We'll be okay with that. We see that we have a product rule that we have to do. So our dA dt is equal to our first times the derivative of the second, plus the second times the derivative of the first, 1/2 dx dt. So tidying up here, we've got dA dt equals 1/2 x dy dx plus 1/2 y dx dt. Oops, that's a t, not an x. Sorry, I misspoke. Then we get to plug in our values. Keep my stuff consistent here. And I have dA dt equals 1/2, x is 9. dy dt, we found up above, is negative 1.5 plus 1/2. We've got fractions and decimals going on here, but we're okay with that. Our y value, which we found up above, is 12. And our dx dt was given at the very beginning is 2. So we've got a negative 6.75 plus 12 gives us 5.25, and our unit on area is feet squared, and our time unit is seconds. Now, for this one, I actually drew the boxes so we'd have them here to use, because we really do want to work on keeping our stuff organized, finding out what is it we have, how do we use it. So we're back to that rocket ship going off. We have our camera over here, and 3,000 feet away, we have a rocket shooting up into the air, my little rocket. From where it is launched, when the rocket ship is 4,000 feet high, its velocity is 880 feet per second. I'm not going to put that in my always box because that's not an always. It doesn't stay at 4,000 feet in the air. What we want to know is how fast must the camera elevation angle change. So we've got our camera moving to look at this rocket. So it's got to go from looking straight across to the launch pad, and instead look up to where the rocket is, so I'm going to call that angle theta. So, but down in my find and when box, I'm trying to find how the angle is changing. So the change in the angle with respect to time, d theta dt, and when the rocket is 4,000 feet in the air, I'm going to call this side y, I'm going to call this side x, and we'll call that side z if we need to again. And the velocity, the rate of change of the rocket, dy dt, is 880 feet per second. So we're finding the d theta dt. The equation we're going to need to use, well, we do have a right triangle again. It's a reasonable assumption to say it's going to go straight up in the air, so it's a reasonable model to use Pythagorean theorem. It's not going to help us to get that theta. We're going to need to have an equation that's got a theta in it. So we're going to come back to, in geometry, again, when we first studied trigonometry, we had SOHCAHTOA. And we used that to remind ourselves what the relationships of the sides were for the sine, the cosine, and the tangent. Well, we are given our x value. At some point in time, we're going to know our y value. So relative to our angle theta, our x and our y are our opposite sides and our adjacent side. So if we've got the opposite side and the adjacent side, we're going to use tangent. So the tangent of that angle is the opposite over the adjacent. And again, I chose tangent because the two sides that I know something about or will know something about are our opposite side and our adjacent side, our y value and our x value. Right now I don't know anything about z, so there's no reason to include z. So I've got that the tangent of theta is our y over our x. Well, up above we said if there's something that's not changing, if there's a value that's not changing, I can go ahead and put that in. And x is not going to change. My camera isn't going to get closer to the launch pad, so I've got y over 3,000. I now need to take a derivative, and it might be easier to think of this y over 3,000 as being 1/3000th of y. Or you could even multiply each side by 3,000 if you wanted to. But when I take the derivative of tan, I've got 1 over cosine squared theta d theta dt. And then on this side, a coefficient times y. The derivative is still the coefficient times dy dt. Now it's time to plug some stuff in. I'm going to do this a little bit the harder way. Right now, it would actually be easier if I multiplied each side by that cosine squared theta, so I didn't have to undo that later, so I didn't have to divide by it or something. But I'm going to do it the harder way, so we see it the harder way. The 1 over cosine squared theta, I don't know. I'm going to have to come back and find that. My d theta dt is what I'm trying to find. 1 over 3,000. And dy dt is given as 880. So this value, this 1 over cosine squared theta, I need to find 1 over cosine squared theta. Well, I'm going to start with trying to find cosine theta. If I look at my triangle again, at this moment in time, this doesn't quite fit in my box, but that's all right. At this moment in time, here's my theta. This is 3,000, and at this moment in time, this is 4,000. So either by Pythagorean theorem or recognizing that we have a 3, 4, 5 right triangle, we see that that must be 5,000 feet. And cosine is the adjacent over the hypotenuse. So if I need the adjacent over the hypotenuse, that's why I came and found the hypotenuse, my cosine of theta must be 3,000 over 5,000, which I can reduce to being 3 over 5. Cosine squared theta then must be 9 over 25, square each side. And 1 over cosine squared theta, I took the reciprocal of this side, I'll take the reciprocal of that side. Now, back here, if I had multiplied each side by cosine squared theta, I wouldn't have to take that reciprocal because I would just have cosine squared theta. But as I mentioned earlier, I'm doing it the harder way. So my 1 over cosine squared theta is 25 over 9. Now, in order to get this d theta dt by itself, I'm going to multiply each side by that reciprocal, 9 over 25, and that gives me d theta dt equals, on the top I've got an 880, and I've got a 9. On the bottom I've got 3,000, and I've got 25. When you put that into your calculator, you've got to be careful that you put parentheses around this bottom. You can put them around the top as well, just for safety's sake. Because if you put in this times this divided by this times this, your calculator isn't going to realize that the 25 you meant for it to be on the bottom. So we now have d theta dt equals 0.1056, and the units measure of theta is radians per second. Why is it radians? Easy answer is because we're in calculus. The more in-depth answer is that because we have taken a derivative of a trig function, our derivative rules are based on our angles being measured in radians. So if we've taken a derivative, we know that we have to be in radians. So again, the easy answer is we're in calculus, so we're using radians, unless we're specifically told otherwise. But the reason is because of our derivative rules. So hope that helps. Good luck.